So I just want to acknowledge first Yuzhang Zhu. He's currently doing a postdoc in my group, but he worked with Dr. Chongwen Zhao and did a lot of the modeling work, or almost all of the modeling work that's presented here. And there's some work done by Shijun Dong. He's a professor now in Wuhan, the origin of COVID. But he's a lecturer there, a professor there, and he did some study that I'm going to be talking about, and others helped with this too, all acknowledged here, Ahmed, Mohammed, Snehashish, and Emrit. Okay, so I'm going to flick through here fairly quickly. I think we all know we're hooked on hydrocarbons and oxygenated hydrocarbons. We want to get away from that, zero carbon fuels. So the idea is to look at ammonia as an alternative, okay? And it's the second most commercialized chemical in the world. There's massive production of it annually, so there's great potential because it's a hydrogen source and it has fuel. So the perspective in fueling gas turbines and heavy-duty internal combustion engines for cleaner power. Okay, so different people are looking at it, and we could be used, for instance, in marine engines also. Okay, it's relatively unreactive. But if it's blended with hydrogen to increase its reactivity in possibly a mixture of 75% ammonia, 25% hydrogen is optimal, and something around that. So we need to understand the chemistry to develop combustors with higher efficiency and lower NOx emissions. And the thing is that if you have NH3 in the fuel, you're going to get more NOx. That's a problem. Okay, but actually, so coming into this study, why do another study? Because first of all, there wasn't a lot of work done on ammonia, or there was work done, we'd say, maybe 20, 30 years ago, and then not a lot for a good few years. But since 2015, 2017, the last 10 years or less, there have been a lot of studies performed, and I synopsize them. But here are some 4 sort of prominent mechanisms in the literature. One from Zhang, which was, I think, Sarathi's group in KAUST. One from Otomo, 2018, University of Tokyo. The Polimni mechanism from Alessandro Stagni, 2020, and Peter Glarborg's mechanism from 2018. Okay, and they each have different symbols here. So I'm just showing you here ignition delay time predictions for pure ammonia, then flame speed predictions for ammonia hydrogen mixtures, and then species N2O mole fraction predictions for pure ammonia with 10% hydrogen, and then with, pure ammonia, 10% hydrogen and 30% hydrogen, okay? And you can see actually this mechanism from Zhang, from KAUST, does a good job of capturing the flame speed and the N2O fractions, but against these ignition delay times, it's too fast, particularly at higher pressure, all right? And then if we take the Ottoman mechanism, okay, it does a better job against the ignition delay, still a bit too fast at all conditions, a very good job of the ignition delay, the flame speed, but then it over predicts the N2O profiles here. Okay, that was the Stagni mechanism, I should say. Okay, the Otomo 2018 mechanism does a really good job of predicting the ignition delay times, but isn't so good at the flame speed, and again over predicts the N2O. And then the Glarborg mechanism, okay, and it does a reasonably good job, but it under predicts the reactivity here, over predicts it here, over predicts the flame speeds, and over predicts the N2O. Okay, now that's a little bit unfair. I just want to comment. Peter Glarborg's mechanism was a Progress in Energy and Combustion and Science paper, and they were just publishing the Ray constant as is. It was never tuned. Okay, so that's just the performance of it. All right. So And then that's all four mechanisms together, and you wouldn't be able to see anything if I showed you that at the start. So I didn't want to do that, okay? So then, but there's been a lot of studies on ammonia, and then ammonia hydrogen, ammonia methane, ammonium DME, and ammonia and heptane. And there's more and more coming out all the time now because people are studying ammonia more and more, all right? But vast majority of these studies you'll see are from 2019 onwards, okay? There's one here, 2015, 2013, but all the others, 2019 and onwards, okay? And then same here, 2015, but most of the rest of them are onwards, okay? And so, and then we have speciation data here as well. It's just a synopsis of the data. So we have the different subsets, but of chemistry, okay? But we have these species, then we have nitrogen species, nitroxide species, and from fuel radical recombination, we get N2H4. I can't think of the name of that now, but it has a specific name. But most of the thermochemistry data that we have for all of these species is adopted from a study that was done by John Bugler in my group, okay, who did an averaging method to calculate the thermochemistry, okay. So the mechanism that we have involves 39 species and 306 reactions. Don't worry about the mechanism details. Really, what I'm here to talk about today are the important reactions, not the specific mechanism, right? And these reactions will be in most of the mechanisms, if not in all of the mechanisms that I've been talking about. But I'm going to show the results from Yu Zhang's mechanism because I asked him to help me prepare the slides that for these summer school lectures that I give. Okay, so I showed you for alkanes, we have high temperature mechanism for hydrocarbon unimolecular decomposition, H atom abstraction of the fuel, alkyl radical decomposition, alkyl radical isomerization. We have exactly the same reactions can happen for ammonia also. So we have unimolecular fuel decomposition, H atom abstraction from the fuel, and then the other reactions, okay? Just like you have in an alkane, okay? This slide I like because here we have the hydrocarbon fuel picture that I've been sharing with you all week, okay? And here we have the ammonia fuel picture. So we have some pyrolysis and then we have oxidation. So the pyrolysis mechanism is here on the left, the oxidation mechanism is here on the right, but this is sort of the complete mechanism for ammonia. And then we can have interaction chemistry, right? So the hydrocarbon fuel can undergo H atom abstraction from the ammonia radical, giving us the alkyl radical of the fuel plus ammonia back again, right? And that's very important. I'll be talking about it a little later, okay? But it's very important to have that rate constant right in the mechanism, okay? The alkyl radical can react with NH2 to give us products. And then we have other NO, so the emissions chemistry that has been studied for a good few years now and is pretty well known in the community. Okay, so you have alkyl radical reacts with NO2 to give RO plus NO. Then we have RO2 plus NO giving us RO plus NO2. So we have all these reactions that can happen. Okay, and this is the R plus NO2 that I was talking about. These reactions can happen. Okay, so it's just showing like if you have a dual fuel, then we have to consider these interaction chemistries in the models if we're going to get the chemistry right. Okay, but I'll show you something that's really nice. I think just try and remember at the end, right? Dual fuel. If we have a lot of these reactions in there anyway, then the dual fuel chemistry reactions, we have to make sure that we add this one, okay? Which is whatever other fuel you have reacting with the ammonia radical, giving us the alkyl radical plus ammonia back, okay? That's very important, okay? So let's look at unimolecular decomposition from the fuel in ammonia, okay? And here's some sensitivity to profiles. And you can see about the only reaction that's of any interest here, these are these are ammonia mole fractions as a function of time at different conditions measured by Eric Peterson and his group at Texas A&M University, right? And what we see is that the only game in town is ammonia decomposition. So if we get that right, we'll be able to get the profiles right, okay? And so then what we were looking at, we have rate constants here. So there's a Davidson and Ron Hansen measurement from 1990. Goes back a long way, actually. Remember I said it was studied before and then it was dropped for a good few years and then it came back. Okay, and so the dotted line is the rate constant recommended in the study by David Davidson and Ron Hansen. And then the red line is the rate constant that we use, okay, in our mechanism. And then these are two other rate constants from the literature also, okay? But by taking that red line data, we were able to get the solid line prediction of these data, okay? And then we have other profiles here too, okay? What am I trying to see here? The red line is the experiment, the solid line is the simulation, and then I think that's a factor of 2, increase in rate constant and decrease in rate constant. No, sorry, it's not. The dashed line is taking the Davidson rate constant, okay? The dashed line is taking the Altenay rate constant, and the dashed dat line is taking the Stagny rate constant and simulating these data, okay? And you can see that the rate constant that we're using best matches the data. Not always, right? But on average, it's the best in simulating all the data. Okay, so that's the rate constant for that. Then we have ammonia undergoes H atom abstraction to give the radical plus RH, okay? And then we have NH2 produces NH, and then NH produces N. Okay, so there's a kind of spiral down. Okay, so if we look here at high temperature ignition delay time analysis, and we do an analysis at this point here, at this temperature, and for this mixture here at this temperature, what we've plotted here, we've 3 different conditions actually. Okay, 1.4 atmospheres and this temperature. What we see basically is that we see high sensitivity in decreasing reactivity to the reaction of ammonia plus H giving NH2 plus H2. Why? Because the fuel plus H will inhibit reactivity. And not just any alkane, but ammonia too. Why? Because it's competing with H plus O2 giving us O plus OH, right? So number 1, inhibiting reactivity is that reaction, right? And then also we have reaction, the NH plus H giving N plus H2 is important. And and actually it should be there, NH2 plus H, is it there? Okay, it's not, I can't see it. Okay, anyway. And then if we look at ammonia flame speed, again, NH3 plus H decreases reactivity, and NH plus H, giving us N plus H2, decreases reactivity. This time it's actually in the same direction. Okay. So, I'm sorry. And we also have then, here we have NH2 plus H giving us NH plus H2. Okay, so if we look at these reactions, NH3 plus H, NH2 plus H, and then NH plus H, you can see that there was some measurements of this rate constant and then calculations of it. And we're using the rate constants from Wen et al. For this reaction in our mechanism. Okay, for NH2 plus H, there's some measurements, and you see here the measurements from Roderick et al. From 1994 seem to be low. We're targeting the Davidson 1990 data for that rate constant and then kind of pinning it to the Bang et al. 2009 low temperature ray constant. And then we have this. This is actually Elisav et al. Calculated this ray constant, and we increased the activation energy by a half a kilocalorie per mole to decrease the reactivity such that we matched the Davidson, and we came closer to the experimental measurement here too, at low temperature. Okay, and then for NH plus H, there is only one measurement in the literature, and we're using the ray constant from Yeo et al. From 2014. Okay, one theme in the ammonia chemistry that I'm showing you is that the data is thin on the ground because the community hasn't been looking at ammonia for very long. Okay, so but this is the best we can do with what we have. Okay, and again, we're doing the usual. Now we are doing some quantum chemistry calculations too, but they take time. Okay, this is a lot faster. Okay, but the data is thin on the ground. Okay, now then if we look at NH2 plus NO giving NNH plus OH, that produces radicals, so that would be chain branching, and then if it gives N2 plus H2O, that will be inhibiting because you're getting stable molecules. Okay, so one channel, this is kind of a branching ratio effect. So again, at the same condition, if we look at our plot, the channel producing N2 plus H2O decreases reactivity. The channel producing NNH plus OH enhances reactivity. That makes sense because of the radicals. Okay, and again, if we look at ammonia hydrogen mixtures, we see in this case it's even more important. This is the most inhibiting reaction is NH2 plus NO given N2 plus H2O. And the second most important reaction in promoting reactivity is that one. Okay, so it becomes even more important for ammonia hydrogen mixtures compared to just pure ammonia. Okay, and again, to flame speed, those reactions are important, right? And both in pure ammonia and ammonia hydrogen mixtures. Okay, and where are we taking the ray constants from? Okay, so we take this ray constant from Sung et al. From 2002. Why? Because it suits us. It fits the data best, right? Here's the Sung et al. Ray constant. Here's some measurements from different groups. I'm not going to point them all out, but it tends to match the data reasonably well. There's a calculation here by Miller and Klippenstein going back to 2000. It goes through some of the data points. Some recent calculations from Stephen Klippenstein it's a little bit faster than the measurements, okay? And so we're using the red solid line. But you can see actually within, and that's because by tuning the mechanism, that was the best fit we got to all the data that we have, okay? This is then just showing you the total ray constant, and you see again the total ray constant goes through the data points. It's a bit slow against these data points at high temperature, but the Klippenstein ray constants are actually a little bit fast against the data. So something in average may be better. And then if you look at the branching ratio, you can see actually we're matching the branching ratio very well. Stephen Klippenstein's calculation, the branching ratio to NNH plus OH is a little bit over-predicted, okay, from his calculations, okay? And that branching ratio will be important in getting the reactivity right because you saw the big sensitivity to both reactions. So if you get NNH plus OH, you get a lot of branching. If you get N2 plus H2O, you get termination and less reactivity. Okay, so now we have NH2 plus NH giving us N2H2 plus H, and then N2H2 giving us NNH, and then this other reaction giving us N2H2 plus R giving us NNH plus RH. They're all important. Okay, and again, at the same condition, okay, we can see that NH2 plus NH giving us N2H2 plus H, that enhances reactivity. Why? Because we produce H atom. And then H atom can go on to react with O2 to give O plus OH, enhancing reactivity. Okay, here NH2 plus NH, same, it's enhancing reactivity. Here it's enhancing reactivity. Okay, and where do we take it from? This is a calculation by Stephen Klippenstein, and actually here's the Davidson et al. Ray constant. Okay, and we actually had to go lower, not higher, to get good agreement with our model. Okay, so Stephen's calculation says the Ray constant should be higher than that determined or backed out by the Ron Hansen's group, basically. And we say it needs to be a bit lower. But by going lower, actually, it's more in line with the experimental data. But again, there's a dearth of data. There's only room temperature data, really. That's it. We don't have anything else to go on. Okay. And then N2H2 giving NNH plus H, that also enhances reactivity. Why? Because we get H atom. The N2H2 reacting with NH2 doesn't allow NH2H2 to produce H atom, so it's going to inhibit reactivity. And here it's actually reacting with H to give NNH plus H2. So that's actually killing you twice, right? Because not only are you not getting the H from this reaction, but you're actually consuming a H, okay? So it makes it a double whammy in many ways, okay? And where are we getting that Ray constant from? We're taking it from Dean and Boselli, okay? But Dean and Boselli had a rate at 1 atmosphere and a Ray constant at 10 atmospheres, okay? So their Ray constant here is the black dashed line and the solid black line, right? So what we did was we really fitted this in p-log form. But you can see our p-log matches what Dean and Boselli suggested for that Ray constant. Okay? And then we can then calculate it at all sorts of temperatures. Okay. Okay, so I don't know. I'll leave it at that. Okay, I'm not going to talk about here. Here, we're taking a Ray constant for N2H2 plus H. This is just a pure fitting. It's from Lee and Cerati from 2020. Well, sorry, this isn't a fitting. This is a calculated Ray constant from quantum chemistry. Okay, and here, this is from Devart and Katwar from 2020. Again, this would be a calculated Ray constant, but there's no measurements at all. So there's nothing to go on and to test to see whether the Ray constant is right or wrong. Okay, so you can see here that the data is very thin on the ground is really the problem. Okay, for ammonia hydrogen mixtures, we see very high sensitivity to NH2 plus O giving HNO plus H. That decreases reactivity. And here again, NH2 plus O giving HNO plus H, it decreases reactivity. Why? Because if NH2 reacts with NO, it'll give us NNH plus OH, or if it reacts with NH, it'll give us N2H2 plus H. Okay, and so if NH2 is reacting with O and not reacting with these other moieties, it's going to decrease reactivity. Okay, so that's the reason why there. Okay, and also it's important here. And again, there was a Ray constant calculated by Sumanthi and Wen from 1998, and we've increased that by 30%. Okay, the reason we've increased it by 30% is we needed to, right? But by doing it, again, there's room temperature data measurements, and we're actually going in the right direction. We're approaching the experimental measurements. And here, Duane and Page did ab initio calculations of the Ray constant. Here's Dean and Boselli Ray constant from an estimation, okay, from 2000. So we're taking the ab initio calculation and using that in our mechanism, okay? Okay, and then HNO giving H plus NO increases reactivity. HNO reacting with H reduces it, and then ammonia plus NO giving NH2 plus HNO, that reduces it, because I think it actually happens in the reverse direction. Okay, so here we have HNO giving us H plus NO. Zhang et al. Published this in 1991, ray constants for this. So we have a 1 atmosphere, 10 atmosphere, and 100 atmosphere ray constant from Zhang et al. And then Stagny calculated it in 2020, Alessandro. And here's the ray constant. And we're using Alessandro's ray constant in our mechanism. But again, there's no measurement. We have nothing to go on. Okay, we're just taking the calculated ray constant from Stagny. Okay, here's another one: ammonia plus NO giving HNO plus H2. Here's a calculation from Zhu and Lin. Another calculation from Mebel et al. Both quantum chemistry calculations. We're taking the more modern one, but again, there's nothing to go on. No data. Okay, and for HNO plus H giving NO plus H2, we're taking this calculation from Wen et al. From 2004. Okay, there's another, the microcanonical one should be more accurate than the canonical one. Okay, so we're taking that microcanonical one. But again, there's 2 data points, and we're sort of in between, and there's nothing else on the board, so we don't know what to do. Okay, but again, it doesn't mean we're largely wrong though, because data and the experimental data will tell you something about what you have to do with the model and the ray constants to get the predictions right. So they do help in guiding the choice of ray constant. Okay, and then we have other reactions: NH2 plus O2 giving 2 different reaction channels, and H2NO plus R giving HNO plus RH. Okay, so these need to be added to the mechanism. Okay, and also will be discussed later. So the reactivity promoting reactions then in the system, okay, and reactivity inhibiting ones. This is just a synopsis. Okay, so we have ammonia undergoes H atom abstraction by H that inhibits. Why? Because H isn't freely available to react with O2 to give O plus OH. Okay, and then NH produces H atom, N2H2 producing H atom, NNH producing H atom, all enhance reactivity because they produce H atom. Okay, and then anything that's consuming H atom inhibits reactivity. That's really what this is saying in a nutshell. Okay. Okay, so then low temperature reactions. Okay, so I've spoken about the high temperature reactions. What about the low temperature reactions in ammonia? And here, it's not surprising that the first one we come across is HO2. Okay, so we have ammonia plus HO2 can give H2NO plus OH or ammonia plus O2. Okay, again, sorry, I should go back. This one will enhance reactivity, this one will inhibit reactivity. One is branching, the other is termination. Okay, and you can see here to ammonia ignition delay times, the most important reaction inhibiting reactivity is the molecular formation one, the termination, and then the one forming radicals enhances reactivity. And they're competing, so one is counteracting the other. Okay. Again, if we look at sensitivity to ammonia hydrogen mixtures, again, there's still some of the most important reactions in both promoting and inhibiting reactivity. And so where do we take the rate? There's actually 3 different routes. We can have NH2 plus HO2 giving ammonia plus O2. It can give H2NO plus OH or HNO plus H2O. Okay. The most important routes, though, are the first 2. Okay. And here is the calculation by Klippenstein and Glarborg, and we're taking that in our model. And then here's the calculation by Klippenstein. That's for the ammonia plus O2 reaction. But if we use that in conjunction with the Klippenstein and Glaerborg ray constant for the other channel, H2NO plus OH, the system is simply just too slow. The model always underpredicts the reactivity at low temperature. Okay, so we've had to increase the ray constant here by a factor of 2.5 to get better agreement with the experiment results. We don't like to do that. It's probably too much, right? But it's what we had to do to get the model to perform reasonably well against the experimental results. Okay, and these dashed lines are the ab initio unchanged ray constant branching ratios calculated by Stevens. So basically, the dashed line, am I right? The ray constant to NH3 plus O2, he calculates the branching ratio to be, what am I trying to say? More towards ammonia plus O2, okay? And we calculated that it's more 50-50. It's still more towards ammonia plus O2, but not as much, okay? And hence we're getting more branching in the system and more reactivity. Okay. Then if we look at NH2 plus NO2, giving H2NO plus NO, we're looking at this too. And okay. Okay, and again, these are important reactions in the system. So we have NH2 plus NO2 giving H2NO plus NO that enhances reactivity, and then this one producing N2O plus H2O. It's a termination reaction, it inhibits reactivity. Okay, and we see the same here for ammonia hydrogen mixtures. Okay, and again, we're taking there's two channels. This is the Klippenstein calculated ray constant, the dashed line here. Here are some measurements. And look, fortunately, there's more measurements in this case. And what we've done is we've decreased Stevens' calculation by 10%. 10% is very reasonable in terms of changing the ray constant. And then for the other channel, where are we? The N2O plus H2O channel, we're taking Stevens' calculation. So we've adjusted the branching ratio slightly to decrease the H2NO plus NO channel and increase slightly the N2O plus H2O channel to get agreement with our model. But it's only a 10% change. And that's certainly within the uncertainty. Okay. What about NO plus HO2 giving NO plus OH? And finally, that one has a big effect on increasing reactivity. Okay, both for pure ammonia and for ammonia hydrogen mixtures, right? And actually, finally, we can say, phew, it's actually been measured very well, and we're using the bulge fit to the data here. And we can use that and say, well, okay, at least that's one rate constant that seems to be pretty well known, and we use it without any change in the mechanism. Okay. What about then NH2 plus O2 giving us H2NO plus O and our HNO plus OH? Again, these are two reactions that both actually enhance reactivity because both are giving radicals. Okay, and here we are actually taking, so there was a Henning ray constant which fits their data very well, but we've reduced that by a factor of 2, right? Okay, and here you see the Boselli ray constant for the channel giving HNO plus OH. Boselli is too slow, obviously. Klippenstein calculated this in 2011, but it's about an order of magnitude lower than the ray constants measured by Henning. Okay, but we're using Stevens' calculation here. So we're not using the Henning ray constant. Okay, he's overestimated, or we've I should say, we're using a ray constant that's half of what he measured here. So it's somewhat consistent that we're also lower on the other route too. It certainly balances the branching ratio. Not that both of them are actually enhancing reactivity in this case, but there may be some issues with the Henning data here. Okay, because Stevens' calculation is actually quite a bit below the Henning measurement, and we took an average, something in between, to get good agreement. Okay. And then we have H2NO plus radicals giving us HNO plus RH, where R can be O2, HO2, NH2, or NO2. Okay. And these can either enhance or decrease reactivity depending on the reaction that's being considered, both for ammonia and ammonia hydrogen. Okay. And here we're taking the red line, basically. But again, all we have to go on are calculations. There's nothing to pin the ray constant to. And until those have been measured, we're still largely in the dark and relying on quantum chemistry calculations. But you can see, actually, like years ago, there would have been a rush to measure these because there was no quantum chemistry calculations to calculate them. But now we do. So, and by and large, we rely largely on Stephen and maybe Carlo Cavallati and a few others that are doing these. But there's very few, really, that are doing them. Okay, so this is then reactivity promoting and reactivity inhibiting reactions. If we're producing OH and HO2, we promote reactivity. If we produce H2NO, we promote reactivity. And if we produce NNH plus OH, we promote reactivity. So this channel here, producing NH2 and that reacting with NO, if it produces NNH plus OH, it inhibits. If it enhances, I should say. And if it produces N2 plus water, it inhibits reactivity. Okay. And that's all I want to say on that. Okay. So we have interaction chemistry then, and we looked at mixtures of ammonia with hydrogen. So how does ammonia affect the reactivity of hydrogen, or how does hydrogen affect the reactivity of ammonia, right? How do they interact, okay? And essentially, what we found is that if we do a flux analysis, okay, the hydrogen in the fuel enhances H plus O2 chain branching and promotes reactivity, right? And the ammonia in the fuel, the ammonia initiation reactions with OH and H, and NH2, HNO, and N2O additions with H and O compete with hydrogen, inhibiting reactivity. So this reaction, H2 plus O giving H plus OH, enhances reactivity. H plus O2 gives O plus OH, enhances reactivity. Okay, so anything that competes with these is going to inhibit. So here we have ammonia reacting with OH, inhibiting. Ammonia reacting with H, inhibiting. Any ammonia reacting with NH2 reacting with O inhibits. Okay, and actually what happened here is that we get NH2 plus H actually gives back ammonia once NH2 is formed. So that inhibits reactivity. Okay. Okay, and if we look here, we have something similar this is at intermediate temperatures, really. Okay, and what we see at intermediate temperatures is that intermediate temperatures we get H plus O2 plus M gives HO2 plus M, right? And in hydrogen, at intermediate temperatures, that competes with H plus O2 giving us O plus OH, which enhances reactivity. Okay, so that inhibits at low temperature, or at intermediate temperature, sorry. But at higher pressure, the HO2 chemistry is more important. And you can see then, if HO2 reacts with ammonia, that inhibits, right? The H2O2 that's produced does enhance, but by reacting with ammonia, it inhibits, because you can see here, where is it? You've got H plus HO2 gives two OH radicals, right? So if you're getting H atom from hydrogen, you get two OH radicals, and that's going to enhance reactivity. Okay, and again here, ammonia plus O2 will inhibit reactivity because, well, NH2 will react with HO2 to give back ammonia and O2, and they're two stable molecules rather than reactive species. Not only that, but you're getting ammonia, which will now react with OH and HO2, inhibiting reactivity. Okay, so this is very bad in terms of decreasing reactivity. So that's just showing how the interaction chemistries are affected, okay, in the different conditions. And then in flames, you can see that, again, H atom is all important. This is inhibiting, and H plus OH plus M, giving water, is also inhibiting, okay? But again, ammonia competes with hydrogen for H atoms and O atoms in the flame and inhibits reactivity, okay? And again, it's not unusual because in flame, H atoms are all important. Okay, I won't go, I don't want to, that's all, consistent. Okay, this is just a couple of slides that Heinz Pitch gave me from his plenary talk at the symposium last year, okay? And so he talked about hydrogen-based future fuels, okay? And he has some nice slides here, and he talks about hydrogen flame speed. The only thing I want you to focus on here really is, look, hydrogen flame speed is way faster than that of methane, and ammonia is tiny in comparison to them, all at the same condition. Okay, so why is that? And this is just showing the measurement. This is for hydrogen, and this is actually for methane, right? So if I could just go back one for a second. Okay, so here's hydrogen, here's methane, and then ammonia is 10 times worse, if you want to say that, or, you know. So hydrogen's very fast, here's methane by comparison, and if we had ammonia, it would be even slower. Okay, so that's just showing the flame speed and the measurement of it. Okay. I don't want to go into the details, it's just a nice figure. So Heinz then looked into, well, if we look at, so stoichiometric burning velocity for hydrogen is 6 times higher than that of methane, right? So here, okay. So what causes the difference? Is it a transport effect due to small Lewis number? Is it thermodynamic effect, the high to flame temperature, or is it chemistry, right? So he looked into all of those, and he said, okay, if he changed the transport, it changed the flame speed at the peak here by about 22%, right? If he changed the thermodynamics, it changed it by about 20%. But if he changed the chemistry, it changes it by 420%, right? So it makes a big difference. So it's actually the chemistry that's controlling this effect, is the conclusion, right? So what is controlling the effect? And that's for methane, right? And so what he did was he looked at the chemistry, and he said, okay, actually in hydrogen, okay, hydrogen consumption is chain branching, because if you consume hydrogen, you get radicals and you get H2O released, right? Okay, for methane though, it actually consumes H atoms. It doesn't produce them. So it's not chain branching. And that's why methane, that's net kind of effect, right? So methane is slower, much slower than hydrogen because of that. Okay. And then he looked into ammonia. Why I have this? Because I'm talking about ammonia here, right? So he looked into ammonia, and then what he found was you have ammonia consumption, you've got ammonia plus 2 hydrogen atoms gives NH plus 2H2. And ammonia is down here in comparison to the other two fuels. So really, really slow, right? And what he found was NH radical consumption depends on these 3 reactions, right? The 28% of its consumption is through this one. These are the 3 main ones. There's others, right? And then you have NH plus NO, and NH plus OH, okay? And this one, keep your eye on this one, right? So they're the three elementary reactions, right? And the net reaction of these is that, okay, if you take the middle one, right, and that's somewhat, we'd say, a neutral case. And a neutral case will be that you consume 2 radicals for every ammonia molecule, right? That's kind of a case neutral, right? With this channel here, through that channel, you consume 1 radical for every molecule of ammonia. So that's kind of a positive in terms of increasing reactivity. But this last channel, right, you actually consume 4 radicals for every ammonia molecule. Now, actually, so here you can see, look, you have 2, 4, so that's 2 radicals for every 1. Here you have 2 and 2, so that's 1 radical for every 1. So you could say, well, Henry, what are you talking about here? This should be 3. You made a mistake. I said this to Heinz. I was talking to him this morning because I didn't quite understand this slide, so I wanted to get it right to tell you guys, right? And he said, no, Henry, he said, NO then has to be consumed, and that consumes another radical. So it's 3 plus another one for NO, which is 4. Okay, so just bear that in mind. Okay, so then he did this kind of a stepwise assessment. So he took the baseline ammonia flame speed at the peak, which is 6.6 centimeters per second. It's tiny. Okay, and then he said, okay, if I adjust the adiabatic flame temperature, I can increase the flame speed of ammonia to 10.8 centimeters per second, right? And then if I keep only reactions 1 and to R1 to R3 in the mechanism for NH consumption. So this was 28 plus 13 plus 13. So that's 26 plus 28. What's that? 54%, right? So all the other ones are eliminated. I only change the flame speed to 13.6. So that means that all the other ones actually aren't that important overall in influencing the reactivity of the system. Okay? Is that okay for everybody? Does that make sense? Right? So we're keeping these ones. So all the other ones are gone out of the mechanism. And if they're gone out of the mechanism, then it's not changing the prediction by a lot, right? And then if we neglect the NH plus O reaction, giving us H plus N plus HNO, that's another reaction that's important, right? But if we neglect that, also the flame speed doesn't change by a hell of a lot. But then if we neglect R3, right, the flame speed changes by a factor of 2 almost. Just R3. And remember, in the mechanism, 28% of the flux from NH was going through here, 13% was going through here, and 13% was going here. So the subsequent reaction of H and HNO are important, right? And the fact that HNO was produced and H was produced is having a big influence on the subsequent chemistry, such that neglecting that reaction, right, makes the flame speed jump so much, right? That's by a factor of 2. Yeah.
Producing H and HNO, but R4 reaction, it's producing hydrogen atom and HNO, but still it is called.
Yeah, it's not as much. So this species is very important. I think that's the point. That's the point of comparing this, right? It's this species that's important, coming through other routes, right? And then if we eliminate that, that makes a big difference. Okay, I think that's the point of that, because they're both producing the same product actually. Okay, so I've got to move on. Okay, so I'm running out of time. This was a study performed by Shijun Dong looking at ammonia and N-heptane blends. And what he showed in this study was that if you include reactions of N-heptane plus NH2 giving heptyl radicals plus NH3, you can simulate the data. Really, that's the essence of what he did. Okay? And this is interesting to look at. I think I just want to highlight this. So this is species mole fraction versus time, right? And the black line is N-heptane, the red line is ammonia, and the blue line is temperature. And you can see that initially, okay, there's no conversion until about, I don't know, is that 40 milliseconds, okay? And then N-heptane starts to be consumed, right? You can see, right? But there isn't much change in the ammonia, actually. But when N-heptane is consumed, we get the heptyl radicals, that adds to O2, we get RO2, QOH, O2, QOH, and branching, right? But and when we get branching, we get OH radicals. And then what happens is the OH radicals abstract hydrogen atoms from N-heptane, giving more heptyl radicals, but they also abstract hydrogen atoms from ammonia, giving NH2 and water, right? But the NH2 radicals then abstract a hydrogen atom from N-heptane, giving us back NH3 and the heptyl radicals. And the heptyl radicals go on and go to chain branching, giving more OH, okay? So what we see is here, look at the ammonia. It dips a bit, so N-heptane starts to be consumed, we're getting OH radicals. No ammonia consumption yet, until the OH radicals build up. Now ammonia kind of falls a little bit, maybe 10%, and then plateaus again for a long time until the time here at which all of the N-heptane is gone. And it's only when the N-heptane is gone that ammonia starts to go. Why? Because ammonia does undergo H atom abstraction by OH to give NH2, but then NH2 abstracts from N-heptane to give NH3. So NH3 it's in a loop. It goes to NH2 and then back to NH3, NH2, NH3, NH2, NH3, until the other fuel is gone, because NH2 is reacting with the other fuel. Okay, and it's only when the other fuel is gone that ammonia starts to be used up. Okay, and then so ammonia inhibits the reactivity of the other fuel in this way. Okay, in the mixture. Okay, because it's competing with the fuel for OH radicals, right? Ultimately. Okay, so and that's what we see here. So where am I? Yeah. So here are the ignition delay times for pure N-heptane. Here's when we have 80% N-heptane, 20% ammonia, and here's when we have 60% N-heptane, 40% ammonia. So you can see that the more ammonia we add to the mixture, the less reactive the mixture is. Okay? And that's pretty well predicted by the model when you consider the facility effects. The dashed line are the facility effects simulations. Okay? So that's that. We did the exact same thing here. This hasn't been published, but this is work we've done in Galway recently. Okay, so we looked at ammonia and decane mixtures. Here we have pure ammonia. Here we have 99% ammonia, 1% and decane. Here we have 95% ammonia, 5% and decane. Here we have 80% ammonia, 20% and decane, and here we have pure and decane. And you can see the model without those reactions in there, the N-decane plus NH2 reactions, is under-predicting the reactivity, okay? Its prediction is too slow. But when we add those reactions into the mechanism, then it fits. We didn't add anything else, just those reactions into the mechanism, okay? So it's the big game in town. When you have binary mixtures of one fuel with ammonia, if you add the fuel, H atom abstraction from the fuel by NH2, then you should do well in predicting the reactivity. Okay, that's the message. Okay, and then there have been lots of studies, they're in your notes, of different fuel plus NH2 studies, a lot of them in the very recent past. Okay, and there they are all synopsized for you there. I'm looking at interaction chemistry, and I've run out of time, but very quickly, if you add NO or NO2 to a fuel, what happens is the reactivity decreases at low temperature and is enhanced at high temperature. Why? Okay. And what happens is basically, if you add NO at low temperature, what happens is it reacts with the alkyl peroxy radicals, forming alkoxy radicals. And if the RO2s form alkoxy, they cannot go to QOH, O2QOH, and branching at low temperature. So at low temperature, it inhibits reactivity. Okay? But if we get RO radicals at high temperature, these are alkoxy radicals. They will give you formaldehyde plus another radical. And formaldehyde, as I said to you before, will be reactive because it'll give you formal and it'll give you H atoms, ultimately. Okay? So, and that's a large part of the thing. Also then, the NO, sorry. What am I after doing? Go back. Sorry. The NO2 formed, or the NO2 that would be in the system if you added NO2 and not NO, right, will react with the alkyl radicals that are formed originally to give you alkoxy radicals plus NO. So there's a kind of if you see here, there's I don't know, an interdependence of these two with one another. If you add NO to the system, NO is going to react with, I did it again, apologies guys. NO is going to react with RO2 to give RO plus NO2. If you add NO to the system, NO2 to the system, NO2 will react with R to give RO plus NO. And then the RO will react with the RO2s to give you RO plus NO2. Okay, so either way, both of these reaction channels will be identical if you add NO or NO2 into the system. And typically what we see is we see the same effect of adding NO or NO2. We see a reduction in reactivity at low temperature and an enhancement of reactivity at high temperature, right? Reduce because you kill the low temperature chemistry by reacting with R or RO2 radicals, producing RO. And then the RO cannot decompose until you get the high activation energy barrier to the beta scission, okay? But when that happens, you get lots of formaldehyde, and then that'll enhance reactivity at high temperature, okay? So that's the effect of those. And then N2O really doesn't have much effect on reactivity. And I think I'm going to leave it at that, okay? Thanks very much for your attention, and thanks for all the attention during the week. Okay, and best of luck. Thanks.